This is a quick lesson on orthogonal projections, section 6.3 in our textbook. Recall from class that an orthogonal projection, if we have a vector y, subspace in a subspace W and Rn, then there's a vector y hat in that subspace such that y hat is a unique vector in W in a subspace for which y minus y hat is orthogonal to the space W, and y is a unique vector in W that is closest to that given vector y. Here is a theorem for the decomposition. We want to find an orthogonal decomposition. We're going to let W be a subspace of Rn. Then for each y in R that may probably not be in W, we can write uniquely in the form y minus or y equals y hat plus z, where y hat is in W and z is not only not in W, but it's in W perp. So z is a vector that is going to be perpendicular to W. In fact, if u1 through up is an orthogonal basis for W, then it turns out that y hat, that vector that's in W, is going to be equal to some constant times u1, and basically a linear combination of these vectors, the basis vectors of W. And the constants, or the weights, in that linear combination would be these projection vectors, projection component vectors. And then z, if you solve for z here, it's just going to be y minus y hat. So the vector y hat is called the orthogonal projection of y onto W. And then we usually write projection of y onto W. So that's how we say it as it's written here. Here's an example. We want to write v as a sum of the two vectors in a span, as a sum of two vectors. One of them in the span of u, and then the other one in the span of u, u1, u2, u3, and u4. So we're going to split up these vectors. So these vectors, they kind of look like, they are linearly independent, so they span all of R4. But what we want to do is we want to split this up into two subspaces, one of them spanned by U only, and then another subspace spanned by U2, U3, U4. And what we want to do is we want to project V onto the span of U1, and then we're going to project V on the span of U2, U3, U4. So first let's project it onto the span of U1. Well, that's pretty much like projecting it onto the vector U1, or the line spanned by U1. So it's really just U1, and then we have V dotted with U1 divided by U1 dotted with U1 along the line U1. So that's just 2U1. And now we want to project it onto the span of U2, U3, U4, and so we essentially just use that formula from the theorem, and then we get values for our weights. We get 3/7 times U2, 12/7 times U3, and -8/7 times U4. Now, if vector V is to be written as a linear combination of these, or the sum of these two these vectors, then we should be able to write V as 2U1 plus all these other terms over here. And then you can double check that if you multiply U1 times 2, U2 times 3/7, U3 times 12/7, and then U4 times -8/7, add it all up, you should get the value of V. Let's do another example. where we want to verify that U1, U2 is an orthogonal set, and then find the orthogonal projection of y onto the span. So this is pretty much the same problem, except the first part is just simply asking us to check whether they're orthogonal. So if you take the dot product of U1, U2, you're going to get -12 plus 12, which is 0. So they are indeed orthogonal. So now let's project it using the theorem. And it's essentially the constants times U1 plus the constants times U2. And these constants are taken by doing the component projection. We're going to get 30 over 25, -15 over 25. And that simplifies to this. And so the projection is 6, 3, 0. Now, if we take a closer look at this problem before we started, we can see that U1 and U2 are essentially, if we take a look at this as in 3 dimensions, the x, y, z space, the z is equal to 0, so U1 and U2 are actually vectors on the xy plane. Y is a vector that's not on the xy plane, but if you look at the projection result that we got 6, 3, 0. That's the same x and y values, except instead of going down -2, we get 0. So if you imagine the U1 and U2 vectors on the xy plane, and the y vector, it's -z, so it's actually pointing down below the xy plane. Your projection 6, 3 would be the shadow that this would cast on the xy plane if it were if the shadow was coming from the bottom. So if we subtract these two vectors, the y vector and the y hat vector, we're going to get 6 minus 6, 3 minus 3, so that's 0, 0, and then -2 minus 0, so that's just going to be a 0, 0, -2 vector, which is a vector that is in fact perpendicular to the xy plane. Now this section introduces us to the best approximation theorem, which essentially says that the vector y hat, which is the projection onto W, is going to be the best approximation to the vector y that you have. So if we take a look at, I'm going to backtrack, take a look at this example again, and we see that 6, 3, -2 and 6, 3, 0, 6, 3, 0 is the best approximation to 6, 3, -2. So in that case, we have, that's going to be the vector closest to 6, 3, -2 that's confined within the xy plane. So that's what the best approximation theorem is. So essentially what this is saying is that when we're asked for the best approximation, we essentially use y hat, the projection formula. So here's our example. Find the best approximation of z by the vectors of the form c1, v1, and c2, v2. Essentially what they're asking us is that imagine v1 and v2 span a subspace W, then z being projected onto v1, v2 would look something like this, a linear combination of v1 and v2, and then this is going to be the best approximation. Well, essentially what we're going to be doing is we're going to be solving for c1 and c2, and again we're going to use that same formula where c1 is going to be z dot v1 divided by v1 dot v1, and then c2 would be z dot v2 divided by v2 dot v2. So those c1 and c2 values, the weights that you get, would be basically 1/2 and 0, and then so this is the value that we get. So just as a note, we can find the distance between the z vector that we have originally and the y hat vector that we found that's in the span of v1 and v2. And then this is going to be the short, if we find the distance between these two, that's going to be the shortest distance that we can find. One last theorem. This theorem relates the projection with matrices. So if we have vectors u1 through up, as a set of an orthonormal basis for the subspace of W, then the projection of y onto W is going to be equal to just y dot u1 times u1, and then all the way up to the last one. So notice there's no u1 dotted with u1 in the bottom of this, or up dotted with up with the last term. That is because it's an orthonormal basis, which means the length, the magnitude, is equal to 1. So if U as a matrix with column vectors u1 through up, then another way to find this projection would be to take a look at the projection of W onto Y, and these coefficients can be built up from U times U transpose. Okay, so we kind of sketched the proof, or part of the proof, in class. So let's just go ahead and give a shot at doing an example. So here's an example. We have y and then u1 and u2. So u1 and u2 look like they're orthonormal. If you look at the lengths of these things, the length should equal to 1. And they, if you take the dot product of them, looks like they dot to 0. So the problem is asking us to first compute ut times u and u times ut. So given that u has column vectors u1 and u2, and then they want us to compute the projection of y onto w the way we've been doing it before, and then to multiply the matrices, and then after that multiply it times y to see what we get. So let's do part A first. So part A, we want to compute this. So we will let our matrix U equal to these things as our column vectors. So we can write it as U1, U2 to assume that they're actually column vectors. And U2 is going to equal to this. Well, if we multiply U transpose times U, U transpose is this column. It looks like a column vector, but it's really a matrix. And it's a matrix where U1 that has 3 elements and U2 that also has 3 elements are written in rows. So it has 2 rows and 3 columns. And so the matrix U will have 2 columns and 3 rows. So let's say that again. UT, U transpose, has 2 rows and 3 columns, and U has 3 rows and 2 columns. So when you cross them, or when you multiply them together, you're going to get a 2 by 2 matrix. And for this, it seems convenient enough to be able to just take the dot products of these things, because that's what you're essentially doing. And again, these are orthonormal basis vectors, so that when you dot it with itself, you get 1. When you dot it with others, you get 0. Now, doing the multiplication the other way is a little bit more complicated. So now let's get actually a glimpse of what U looks like and what UT, the transpose, looks like. And so if you do this multiplication, you're going to get this 3 by 3 matrix. Okay, so this is our 3 by 3 matrix. Okay, we'll use this matrix in the second part, when we're asked to multiply this matrix with apply the y vector onto this matrix. But we'll get there in a minute. Let's go on to the next part, where we're asked to compute the projection of y onto w. So the first part, projecting y onto w, we're going to use a projection formula. And the projection formula, again, there's 2 u1 and u2, so there's 2 vectors to project onto. And then here are the values. Remember that u1 and u2, we actually didn't need this by the last theorem. That's equal to 1, but I put it there anyway. So in any case, if you take the dot product of y and u1, you get 6. If you take the dot product of y and u2, you get 3. And then you get this vector 2, 4, 5. Now, when you do the matrix calculation, remember that long complicated matrix that we found, this is the matrix U times U transpose, 3 by 3 matrix, and we apply it to the vector y, or we apply y to that vector, we're going to get a 3 by 3 times a 3 by 1, so we're going to get a 3 by 1 matrix. And doing this multiplication, we're also going to get 2, 4, 5. So that's not a coincidence. That is exactly what the theorem was telling us we would get. Okay? So it's best to take a look at the theorem, take a look at these formulas, and then be able to apply these formulas. Okay? Good luck.